And it turns out you can easily find the Q operator for the whole system, which is alpha beta plus beta Q, the same values for alpha and beta. And all we're doing actually shifts x to x plus I alpha and y to y up to I beta, and that gives you this equivalent emission Hamiltonian. So that's the equivalent isospectral Hamiltonian to that one. Now, okay, so there it is. It's emission, but I still don't know its eigenvalues because it's not diagonalized. So I just got to do one little bit more algebra, do a little transformation, and diagonalize it. And that h is equivalent to that, and the new variables x, y, p, and q. And now what I've got is actually two harmonic oscillators. So the whole spectrum is just the sum of two harmonic oscillators. But you see, you've got this 1 plus sigma g here, where sigma is plus or minus 1. So one harmonic oscillator's got a frequency square root of 1 minus g, the other's got a square root of 1 plus g. So altogether, this is the spectrum. And if you take g greater than 1, you're in trouble, or g less than 1. So if mod g is greater than 1, the eigenvalues can become complex. So, and this is really a generic problem, I think, that if you have the thing in isolation, it's got a real spectrum. You've got the emission one, it's got a real spectrum. But if you combine the two, you run into this business that you can't make the coupling too big, otherwise the PT-symmetry is broken and you get complex eigenvalues. And I think that's really a generic situation. So that's not a very good message to end on. But I want to take the last 10 minutes or so to go on to a different subject, which is definitely not concerned with foundations of quantum mechanics, but I think it's very interesting. And that's to say that all these ideas, all this whole machinery of PTs, of metrics and so on and so forth, has found an unexpected application in classical optics, because in classical optics, there's a particular approximation, which is called the Paraxial Approximation, where you finish up with an equation in optics, classical, which looks exactly like the Schrödinger equation, with obviously different meanings for the symbols that occur therein. So you start off with the scalar Helmholtz equation for the component of electric field, and we're thinking of a medium which is the vacuum refractive index, and on 1 plus a little perturbation on top of it. And then you write E, so K is almost equal to K0. So we write e to the ik0 times psi, so this psi is called the envelope function. And then the equation for E translates into this equation for psi. And K squared is K naught squared, N squared over N naught squared. And what you then do is you have a certain situation where the wave is going predominantly in the z direction, and the variation is less in the x direction, is slow in the z direction of psi, and therefore you make various approximations. So you neglect the first term, you neglect the d2 by dz squared. That's supposed to be small. The dimensions in the z direction are much bigger than the ones in the x direction. And then the k squared minus k0 squared is almost 0, but in fact it turns out to be 2k0 squared times v. So what you get, when you've done those approximations, is you find an analog Schrödinger equation for this envelope function psi, which is I d psi by dz plus 1 over 2k d psi by the x squared, that's k v of x psi. So we've got a time-dependent Schrödinger equation, except that z, the longitudinal direction, replaces t, and the role of this is the potential in our analog equation, but where v came from was actually, remember, it's a little addition to the refractive index. So v is related to the refractive index, and this is excess refractive index, in fact. So that can be complex, and it can be made PT-symmetric. And in optics, when you have a complex refractive index, a positive imaginary part corresponds to loss or damping, and a negative imaginary part corresponds to gain. And if you construct some system with loss and gain carefully arranged so that they are in a PT-symmetric fashion, then you get very nice things happening. And this development actually came from people in the optics community, not from people in the PT-symmetric community originally. They saw these PT ideas and thought, okay, we can implement these in optics. So that's what I'm talking about. I'm talking about a wave going through some material with some varied potential, refractive index, and having some scattering or diffraction. So this was the original paper that did this in like 2007. And these opticals have all kinds of interesting properties. And this is a sort of thing that can happen. So what I've got here is I've got an optical potential. This is theoretical. There are actual some later on. I think there are some experiments which have been done. This is the intensity pattern for the optical potential. This optical potential is a sinusoidal potential varying in the x direction, and lambda is 0.9. And it turns out that you'll get lambda. There's a critical value of lambda, which is then 1, where the PT symmetry gets broken. So if you're lambda less than 1, everything is sinusoidal. You don't get any growth or decay. But lambda equals 1 is the critical value. So so what you see here actually is this interesting thing that you've got funny lobes here, and then it's bifurcated. You've got a bifurcation here. And this thing also is not symmetric. If you send the thing back through, you won't get the same. If you send this light back through, it won't do the same thing. It's not reversible. And there's another one actually. I put in a very narrow input here, little Gaussian wave packet here. And that's the sort of thing that happens. Very nice packet. And this one illustrates most clearly perhaps the power oscillations. In other words, the brightness is the intensity. So the intensity grows, dies, grows, dies, grows, dies. But that's because it's exchanging energy with the medium. And that the intensity is not conserved, because it would be the eta intensity that would be conserved, not the actual ordinary intensity. Right. Okay, and that's another one. This was coming in. That's another one. It depends the pattern you get depends very, very much on the angle you come in and so forth. Now, then there's another kind of experiment you can do, which is where you have the modulation of the refractive index going longitudinally in the z direction rather than in the x direction. And this is just a one-dimensional thing. And so now we're going to talk about transmission and reflection coefficients. And in fact, there's no approximation. We don't do any. We just take the equation as it stands. So it's like a time-independent Schrödinger equation, if you like. And we look at various setups. And the first one that was looked at was by these people, which was two waveguides, two coupled waveguides, one with gain and one with loss. And then you just have these rather simple, with a single mode in each one. You get these rather simple equations, which obviously you can solve. You get sinusoidal variation solutions for psi 1 and psi 2, which turn into, and there's a critical value again here of this gamma, which is 1, or kappa really, and then you get linear things exactly at the transition point. This is actually quite interesting. In all these kind when you go through a transition point, you get eigen values coming together and a single eigenvector only. So you get degeneracy, and in that case, so you can't diagonalize the Hamiltonian. You have a Jordan block. So you have one single eigen function and an associated Jordan function, and that gives you, instead of being oscillatory behavior or exponential behavior, which would be beyond the transition, precisely at the transition, you get linear behavior in Z or in time. And above the threshold, they turn into Cauchys and so on. And actually what they did in the first place was they didn't quite do what I said. They added a minus gamma to everything. So that made the one with gain, instead of having one with gain and one with loss, one becomes now neutral, and channel 2 has twice the amount of loss, which is much easier to implement experimentally. So all that happens is that, the previous solutions get multiplied by e to the minus gamma z, so this sort of thing. And if you plot the transmission probability, the total transmission probability, you put the input into the passive channel, so that's the thing which doesn't have any gain or loss. It's coupled to this lossy channel. And what you might think, you start off with transmission coefficient being 1, but then as you add loss to the loss, the funny thing is, it goes down, which is what you expect, so you lose transmission. But at a certain point, kind of near the transition point, near the symmetry breaking point, actually it turns around and then goes up again. So you get this. This is a very nice example of a physical effect that can happen from this breaking of the PT symmetry, and it turns around and then goes up again. Basically, sort of what happens is, beyond that point, is although you've got a lot of loss in the lossy channel, it never gets there. It doesn't. It just stays in the neutral channel. So that was a very nice. This was kind of quoted as a PT phase transition in the paper. And then finally, the other paper which attracted a lot of interest and could possibly this thing could possibly kind of be used in optical devices is what's called the phenomenon of unidirectional invisibility. So this is the general setup we're talking about. Set the equation. And what I want to talk about is the particular case when the potential is right on the transition point. In other words, remember it's cos plus lambda sine, and when lambda equals 1, then that was right on the transition point. And that's the most interesting case, so that turns into a complex exponential. So in their paper, they used the approximate method, and the results they got out of that method was that the whole thing was completely different for left incidence and right incidence. If you had left incidence, then the transmission was 1 in their approximation. You get complete transmission, and reflection was 0. So the whole thing was completely invisible from the left, according to their approximation. This is Fitzgerald letters last year. On the other hand, it's quite different for a right incidence. If you go from right incidence, then you actually, sorry, that's actually wrong. The transmission coefficient is again 1. In fact, the transmission left and right there's a theorem that has to be the same. But the reflection coefficient has this word. I didn't tell you what delta was here. Delta it's called the detuning. It's the difference between k, which is the wave vector, and beta, which was the modulation of the refractive index. So when they're in tune, that's when delta is equal to 0. And this reflection coefficient has this sink form, which can get very big, proportional to L squared, near delta equals 0. It turns out you can do this whole thing analytically. You can solve the whole equation analytically for these coefficients in terms of Bessel functions, I and K Bessel functions, and then now you can. Now this is no approximation. You can now look again at these results, and what you see is exactly as a function of delta. Actually, the transmission coefficient from the left is pretty well 1, but it just deviates a little bit around delta equals 0. And the reflection coefficient is very small, but it has these little oscillations on a very small scale. If you go to the right, I said the transmission coefficient is exactly the same. The reflection coefficient, however, so that's the sinc function, and it looks very much like their expression. So see, it goes up to 15. So this is a huge reflection coefficient. So that's this particular setup has this very interesting property. On the one hand, if you go from the left, it seems to be invisible. That's what they call unidirectional invisible. If you go from the other direction, you get an enormous reflection. So that's okay. So and then there are lots of other kind of setups where people are exploiting these ideas in optics and in other fields as well. So to summarise, as I said, now that the dust has settled, I think it's fair to say the status of PT-symmetric theories with real spectra is understood, and the main component of that is that they are related to a Hermitian system by a symmetry transformation. But in general, that equivalent isospectral Hamiltonian is usually very complicated and non-local. So that would be actually very hard to deal with. In fact, actually, the very, very beginning of this whole story, which is before Bender and co. came into it, was by Schultz and co. And they were working with solid state, and they had a Hermitian problem, a solid state problem to solve, and they made a similarity transformation on it, which made it easier to solve, which actually turned it into a non-Hermitian problem, but they didn't care. I mean, they were just trying to solve the original problem, and that was a means to an end, so it can be useful in that way as well. Usually it's very difficult to calculate Q. The wrong sign quartic is the only non-trivial case where Q is known exactly. But, as I said, for purposes of calculating green functions, we don't actually need Q, and that's good for quantum field theory if you really want to use this in quantum field theory. But the big but is that there, in my opinion, remain severe problems with treating PT-symmetric systems as fundamental. If you treat them as effective theories because you're ignoring some part of the system, that's fine. Nobody can argue, but you can certainly argue with treating them as fundamental because of these problems. And then, as far as optics is concerned, so the original idea of PT symmetry in quantum mechanics found a new application in classical optics. In that context, the more focus actually is on the symmetry breaking rather than the symmetry conserving, or the transition, going through the transition. That's where you get interesting phenomena happening. There's that counterintuitive result for passive coupled waveguides I showed you, where you actually increase the loss, the transmission goes up rather than going down. There's that setup I discussed here with unidirectional invisibility and enhanced reflection. And there are many other interesting results, and this is actually a very active field of research, although it's not research into foundations of quantum mechanics. Thank you very much.
We have time for a few questions. If not, I'll ask something. So I was thinking about time-dependent Hamiltonian.
Oh, yeah.
So what happens if you take a Hamiltonian along a path that starts in a Hermitian Hamiltonian and ends up as a PT-symmetric? Because your inner product is changing as you go through the changes.
Yeah, I believe, I mean, I haven't thought about that very much, but some people have thought about the case where eta would be time-dependent, and I think that causes, that's very, very difficult. To have a time-dependent eta. It doesn't sort of, all sorts of things go wrong. And Mustafa Zadeh thought about that, and Miroslav Znoya. They in fact had a big public fight about the whole thing. and I think what happens actually in these pseudo-Hermitian things is that it's that the Hamiltonian isn't actually the generator of time translations. You have to have an extra little bit added onto it, something like a gauge bit. So maybe you could, if you include this extra bit, maybe it can be done. I don't know. It's interesting.
Yeah. Any other questions?
But this is in that case something similar to what you have in the Paraxial Approximation.
In the Paraxial Approximation.
Yeah, I mean, he was asking whether you introduce time or something. I mean, but I guess that is if you go wrong, if you write that with just as a independent problem, that you can go to optics where you have this Paraxial form, and something similar. You substitute set, that set by time.
Yeah.
It should be the same. I used to get sort of similar solution.
I mean, in fact, you see, actually, in optics, one doesn't really bother about all that stuff. I mean, like the eta. I mean, you just do the calculation, and it has this the transition, which is very interesting. And you don't. I mean, again, it would be very, very hard to calculate the eta. And you don't bother. I mean, you could do, in some cases you can do. For example, if you're doing a calculation and you know that mob psi squared or the intensity squared is not conserved as you go along. But there is something that should be conserved, which is this pseudo thing, and that you can use if you know eta, you can use that to check on your numerical calculations. But by and large, you don't use that machinery at all. You just calculate, the non-Hermitian thing, just integrate.
Something like you transfer all the technology you have in optics to quantum mechanics. For example, one-dimensional quantum mechanical problem, just in time would be equivalent to this two-dimensional problem in objects.
Yes.
Where you have x and z.
Yes, that's right.
X and time.
Yes. But as I said, in general, the machinery, such as it is involves this eta, which is just very, very hard to calculate in all the very simple cases. I think actually, I can't remember. Yeah, in some cases you can use that. I'm not using it as time-dependent or thing, but you can. There are some cases where you can calculate and you can calculate the equivalent machinery. But if you want to. But there's one other place where these ideas, well, actually several other places where these ideas come in. Towards the beginning I talked about this Sturm-Liouville thing on an interval with an IX cubed potential. But prior to that, you can do it with an IX potential, and that has basically the same sort of features where you have things coming together. And that has physical consequences, it turns out, in about 3 different places. One, you get the same equation when you're talking about current going down a superconducting wire. And then that transition corresponds to something interesting happening in that situation. It also crops up in water waves, actually, as well. And in some particular equation for water waves, you get the equation with an IX potential. So it crops up in 3 different places, actually, that particular problem. But in nearly all those cases, what's interesting is a transition from PT-symmetry to PT-symmetry being broken. Yeah.
Okay, I think we should go to the break now, so let's thank you again. We're back at 11:30.